Okay, good morning. Welcome to another morning lecture. So, the last time we finished the class here on a CDN example and Bob accessing CDN networks to stream a video. So, this is an example of streaming over HTTP. So, NetCinema is the server Bob first connects to. So this is like Netflix, where perhaps holds the IP rights to the video and sells the service for streaming. So Bob first accesses netcinema.com's webpage, and then the netcinema.com sends Bob the video file, the URL for the video file. But Bob needs to resolve that URL through his local DNS, which sends a DNS query to NetCinema's authoritative DNS. But the video file is not stored at NetCinema's own servers. So NetCinema's authoritative DNS turns the authoritative DNS server, authoritative content delivery network server, that in fact holds that video file. And then Bob's local DNS sends a query to this authoritative DNS, which is King CDN's authoritative DNS server, which then returns the exact IP address of the King CDN server that holds the video. And then Bob can send an HTTP request and download the video file from the King CDN server. Okay, so this was an example of HTTP streaming content access to a CDN through HTTP streaming. And I also said here that the CDN servers, the King CDN's authoritative DNS server, this guy, performed a very critical DNS task. It performed load balancing. It particularly chose this CDN server to serve Bob. It might have, this King CDN might have many other servers that keeps the same format of the same video file, but it can choose among all these CDN servers, it can choose the best one for serving Bob. Well, there are many approaches to choosing that. It can choose the closest one to Bob, it can choose the less congested one, or it can choose the one with the shortest delay. And we also talked about how these selection methods can be achieved by the information we have. But today, we are moving on to HTTP streaming again over a Netflix case study. So here we have HTTP streaming with Dash, dynamic adaptive streaming with HTTP. So Netflix is, in fact, a lot of the downstream internet traffic. That is about 15% in 2023. So that's a lot, Netflix alone. But the interesting thing about Netflix is that it doesn't, at least it previously didn't own any infrastructure, any CDNs at all. It only hired third-party CDN services. So they're only doing the juicy part of the work. They are selling the videos, but they don't have to do the laborious part of setting up CDNs all over the world and responding to the service requests by their clients. They are using third parties for that. But still, Netflix owns its own payments and own registration servers. This is their preference. It doesn't require too much servers for that. You can just set up a few servers in the US, perhaps, and serve all the people from there. And it uses, Amazon services for uploading the video to the Studio Master, and then Amazon Studio Master converts that video into multiple formats, maybe high resolution, medium resolution, and low resolution formats, and then stores each of these copies on other third-party CDNs. And for that, Netflix uses Akamai, Limelight, and Level 3's CDN servers. These are the CDN service providers, which have thousands of servers around the world. So what happened in the end is that when a user logins to Netflix or enters credit card information, it still goes through Netflix servers. So your HTTP client is talking to Netflix's own servers. But then when you are, in fact, clicking on a certain video, you go to Amazon's cloud server, which then sends you a catalog of videos. And then you can choose which one of these videos, which version of these videos you want to view. And then you're directed into these third-party CDN providers, Akamai, Limelight, and Level 3. So let's see that over an example here. So again, this is Netflix's registration and accounting servers, and here's our Bob. So Bob first registers with Netflix, creates an account, enters credit card information whatsoever. And then Bob is browsing the Netflix videos over the web using his browser, which is served by Amazon's cloud. And once Bob chooses a video, clicks on a video to play, then he requests that manifest file for that specific video. So this manifest file is, again, something like a catalog. So let's say Bob has chosen some video 1, and it will show Bob, for high resolution, go to this Akamai server, or maybe I also have it in this Level 3 server. Well, for the low resolution version, you can always go to Limelight server, or again, I have another copy in this L3 server. So it is a catalog of video formats. And Bob's own client then, or Bob himself, if the client application allows, you can sometimes choose which version of the video you want to stream, then goes to the server he wants to stream the video from. In this case, the Level 3 CDN server. It is a dash server. It is selected by Bob's client, contacted by Bob's client, and then the streaming begins. So if we compare this approach with the previous one here, with HTTP streaming, well, we can see that the intelligence here in the Netflix example is at the client, so the client can choose. But here in the earlier example, it is the CDN, it is the authoritative DNS server of the CDN provider that chooses. So DNS is performing that load balancing action and choosing which video each user should stream. Okay, any questions? Cool. So next, we are moving on to another type of very popular application. This is voice over IP. And in fact, this is the application that you use when using Skype calls, when using WhatsApp calls, perhaps Telegram calls, even in certain cases, Zoom calls. And here our constraints are a little bit different than video streaming. So first of all, we have a very strict end-to-end delay requirement. Otherwise, we cannot maintain the conversational aspect of the voice of humans' interactions. So if we have delay perhaps over 400 milliseconds, it is not even acceptable. And ideally, we want about perhaps 150 millisecond delay at most. Otherwise, you probably had these calls when you talk to someone with a bad network service or someone very far. After you stop talking, only a few seconds later, the other party hears and understands what you said, and then the other party starts talking later, but sometimes you don't know if they are talking or not, so you also speak at the same time. So it's not a good experience. So ideally, we want less delay here. But good thing is that we do not have so much throughput requirement, unlike the video. In video, we need to have at least a few megabits per second, right? Because we are sending video data after all. we need to send the data for the whole screen. But here it's just voice. But there is another thing that we need to communicate here. How do you initialize a call session? In other words, how does the calling party advertise, how does the calling party know, let the other party know that he wants to initiate a call, and how does the callee, the person being called, let her IP address known to the caller? And how do we select the port numbers, and how do we agree on a certain encoding format? Again, similar to video formats, in sound we have multiple formats based on the quality of the network available or the type of application. So how do we decide on all these? So to keep the discussion relatable, let's talk about a specific voice over IP example and see the challenges of voice over IP here. So let's say two people want to talk and establish a voice over IP session. Well, the speaker's audio here will be alternating talk spurts, meaning that I talk for a second, and then I pause, and then I talk for a few more seconds. Nobody goes like, blah, endlessly, right? There are some silent periods. And we can exploit these silent periods, as we shall see later on. So we have about 8 kilobytes per second during a talk spurt. Well, again, why 8 kilobyte? Because we probably sampled we probably quantized each sample with 8 bits. That gives us 256 levels, right? And then that means divide 8 kilobytes by 8, I get 8 kilobits per sample. And that means I sampled about 8,000 times per second, right? And if I'm sampling about 8,000 times per second, that gives me neglectable loss for up to about 4,000 hertz or something like that. I need to sample at least double the frequency of the sound wave I'm sampling. So, well, it captures most of the human sound. So that's why we have 8 kilobytes per second. Well, of course, if you want to build a better application with less loss for each sound wave, well, then you can sample at 16 kilobytes, 32 kilobytes. But the good thing is that this 8 kilobytes per second only occurs when one party is talking. So in between, you do not have to send any packets. So let's say each of our chunks, each packet, contains 20 milliseconds of sound data. That gives us, so this is 1/50th of a second, and 1/50th of 8 kilobytes is what? That is 160 bytes, right? So that is 8 kilobytes over 50, because 20 milliseconds is 1/50th of a second. That gives me 160 bytes of data. I mean, this is how it is calculated, probably. So that means in every 20 millisecond chunks, I need to send 160 bytes of data to my receiver. And of course, this is only the data. I also add certain application layer header to each chunk. Where this packet is headed, what's the port number, if there is an ID to that, what's the ID, if there is a timestamp to that, if there is a synchronization number, what are those, and so on. So that is 160 bytes plus some application layer headers. And then these chunk and header will be encapsulated into either a UDP or TCP segment, which will then be encapsulated into a network datagram and so on. Yeah, and then the application again needs to send into the socket every 20 milliseconds during a clock spurt. But things are not always perfect, as we have seen in the video example. So we will experience packet losses and delays. So if each packet arrives to the receiver with a constant end-to-end delay, then the receiver can periodically play these chunks, a chunk in every 20 milliseconds, and everything is fine. But if the packets arrive with variable delay, well, then that's where things get complicated. We need to introduce perhaps some playback delay, just like we did in the video case, or in a playout delay. But delay is not the only thing. We will experience losses, right? So it can be either due to one of the clients having bad throughput, bad links, or it could be due to somewhere in the network. Maybe a router in the network has its queues full, so that the arriving packets to the full queue will have to be dropped, right? So every router and switch will have a certain amount of queue, certain amount of packets they can buffer. But as these things get full, if another packet arrives, this has to be dropped. So this is also known as buffer overflow. So if we lose some packets, some sound chunks, and let's say we have retransmissions and they arrive at a later time, but when the time they arrive, we have already played the chunks that come after that, that need to come after that. Well, is there any point in receiving this chunk that was previously lost? No, right? You never experience a voice over IP call where some of the things that the other person said earlier are played after some other sentences, some other words are played. It never goes back. So retransmissions here are not that useful unless you can receive retransmissions very quickly before anything else is played. So that's why usually we use UDP for voice over IP, because the retransmissions in TCP are unnecessary and unnecessarily congest the network. But still, if you want to build a voice over IP application with retransmissions, you can still build that on top of UDP in the application layer or on top of UDP in the transport layer. So this was about delay loss. So if we have more delay than our playout delay, we just ignore that sound chunk. But the good thing is that we can still tolerate some loss. Even if you do not hear exactly, you do not reconstruct the exact sound wave that the other party sent, you can still understand the voice signal. So we can tolerate up to perhaps 10%, about 10% packet loss rate. And we have ways to improve the packet loss with certain methods like forward error correction coding and interleaving. And we're going to see those later on. So this is one of our famous figures, cumulative data over time. And this red plot here shows when the server sent each chunk. So this is perhaps first chunk. This is the second chunk. And per our earlier example, each of these chunks are sent at 20 milliseconds intervals. So that is 20, 40, 60, and so on, right? And how much was each data? Can you remind me? That was 160, right? So that is perhaps 160. And this is 320, and so on. It goes on like this. So as you see here, the cumulative data is much smaller than the video's case. And this black plot shows us when we receive those packets at the receiver. Of course, there will be a variable amount of network delay, so we do not have the exact same perfect steps, but we have a more distorted plot here. So the first packet arrived quickly, but the second packet was delayed a lot. And before that, so even if your reception times vary, you still want to play this at the constant bit rate. Again, 160 bytes per 20 milliseconds. Otherwise, the sound will be distorted. It will go faster and slower, faster and slower. It will impact the experience, user experience. So what we can do is we can introduce, very similar to video streaming, we can introduce a playout delay to the client and play every bit a bit late. But again, as you see here, if I set the client playout too low, well, what happens is I will miss some of the packets because they will need to be played even before these packets arrive. But if I choose a very high playout delay, now this will distort the experience because the timing difference between the time between these sound chunks are transmitted and received should be less than about 400 milliseconds, and in the ideal case, they should be less than 150 milliseconds. Now, this is stricter than video. In video, it doesn't really matter if the playout begins maybe 2 seconds after I play the click button. And yeah, same as the video, this green distance here would be our buffered data, how much data you buffer before you play. And end-to-end delays of 2 consecutive packets, the difference can be more or less than 20 milliseconds. So now the problem is, the design problem here is how to choose the client playout delay. Well, there are 2 approaches we can take. First one is the fixed playout delay. You just set a fixed, let's say 80 milliseconds of delay between the time you receive the packet and you play the packet. So this playout delay is, again, the time between you receive and the time you play. Well, in this fixed playout delay, we have exactly Q milliseconds after each chunk was generated to play. So typically, the sender will attach a timestamp T, and then the playout will occur at T plus Q, right? But if the chunk arrives after T plus Q, that cannot be replayed, and it will just be dropped. So here our trade-off is, if you choose a very large queue, you will experience less packet loss, but if you choose a small queue, you will have better interactive experience, yes, but you will have more packet losses, possibly. So this is how it works on our famous graphs. Well, again, the black line here is, the black plot is the time the packets are generated, and this light gray line here is the time they are in fact received. Well, if you choose playout delay of this much, P minus R, as you see here, yes, most of the packets can be played. Yes, you have good experience. But from time to time, if the delay increases, like here, you will miss some of the sound chunks, so they will not be able to be played. But if you push your playout time, if you push your playout schedule into the second plot and introduce a playout time of P prime minus R, then you can play all the chunks. So in the previous example, you saw how the delay and loss trade-off works, right? when choosing the playout delay. So ideally, we want both low playout delay and we want a low loss rate. So our approach here then could be adaptively choosing that playout delay instead of fixing it. You know, if our throughput is good, if our delay between the sender and the receiver is very small, we can fix that playout delay to a low value. But then if it increases, we can increase it with the increasing delay in the network. So this is how we do it. We have this exponentially weighted moving average formula, but again, you can use any other formula. This is, again, not for memorization or anything. This is just an example I'm giving. So let's say Ri is the time we, in fact, receive the packet, and we ask the sender to attach a timestamp to each sound chunk, and that time is indicated with Ti. So what happens if you subtract Ti from Ri? It gives you the measured delay of the ith packet, how much a particular packet, particular sound chunk, is delayed. So now that's our instantaneous delay. You can measure it per sound chunk, per packet, right? But now I'm multiplying that with some constant. I'm assigning it some weight, alpha. Alpha is typically a small constant, like 0.1. And this is a recursive formula. So di is giving me my delay estimate of the ith packet. So my current delay estimate is the delay, the measured delay of the ith packet multiplied with some weight plus my earlier measurement. Again, this is a recursive formula. My earlier measurement, again, multiplied with another constant. And why do we call this exponentially weighted moving average? Well, because in a way, you are measuring the delay of every packet, multiplying with a constant, and then that thing gets multiplied with another constant every interval. So the weight of an instantaneous delay gets smaller and smaller over time. So if we, again, draw the weight of each, so for the current packet, I'm assigning a weight of 0.1, right, assuming alpha is 0.1. But then when I'm measuring a delay estimate for the next one, my two previous packet will have a weight of 0.1 times 0.9. And for the next one, it's going to have a delay, it's going to have a weight of 0.1 times 0.9 times 0.9. So it gets smaller exponentially with a factor of 0.9. That's why we call it exponentially weighted moving average. So this, again, when you think about it, this gives you an estimate of the delay with more weight given to the more recent packets and less weight given to the older packets. Yeah, let me repeat that. Again, this is just an example. You can use other methods. Perhaps you can use machine learning to estimate what the delay will be for the future packets. Yeah, okay, let me ask you a question then here. Is average delay really enough? So let's say I tell you your average delay is X, and X is a random variable. You can calculate this exact value, okay? Sometimes X is 100 milliseconds, sometimes X is 120 milliseconds, sometimes it is 70 milliseconds. But I'll tell you the X. This is your average delay. How much do you, okay, I will not tell you X, but I will tell you the average of X. Okay, so I'll tell you the mean of x, and I'm going to tell you this is 100 milliseconds. Is this really enough for you to set your adaptive playout delay? If the mean of x is 100 milliseconds, how much adaptive delay should you set for the next packet, for instance? Currently, x is 100 milliseconds, but sometimes it goes to 120, sometimes it goes to 140, sometimes 80, sometimes 50. Can I set my adaptive playout delay to perhaps 100? Well, if I set it to 100, x has a distribution, right? Let's say this is the distribution. And this is 100. If I set to 100, my adaptive playout time, well, all the packets that arrive later than 100 milliseconds will be lost. So that doesn't work. Well, perhaps I can just multiply that with a constant, right? I can multiply that with maybe 2, and I set it to 200. But then, only a small fraction of these will be lost. But I didn't tell you the distribution of x. I only told you the mean of x. So what if x instead is a random variable like this? That's 100 here and 200 here. Then you have a larger portion of the packets arriving late and therefore lost. So estimating the expected delay is not enough. I need something else. I need some other information about the distribution of the delay, correct? So, because in this example, I told you the average, and that is not enough. Are you going to set the adaptive playout to twice of that value, triple of that value? Well, the good approach, the one good approach you can take is to also look at the variance in the delay, amount of variation in the delay. Is the distribution a very tight distribution like the first red one? Or does it have a long tail, meaning that it can have very large delay values? So to do that, we also estimate the average deviation of delay, VI. And we have a similar approach here. So if you remember, Ri minus Ti was the measured delay of my current packet, right? Ri is the time when I receive it, and Ti is the time it was sent. So Ri minus Ti would give me the instantaneous delay of the current packet. And what was Di? Di was my delay estimate of the current packet. So if I subtract the instantaneous delay, if I subtract the expected delay from the instantaneous delay, that gives me my measurement error. That gives me my variance in the delay. And I have the same recursive formula, same exponentially moving average formula, and I'm multiplying with some constant, and I'm also multiplying the estimate of the previous variance with a constant, and I'm using this VI as my estimate of the variance in the delay. And then returning back to our earlier question, how much playout delay are we setting? Let's say mean of x is mu, and variance in delay is sigma. Well, what I can do is I set my playout delay to something like mu plus some constant times the variance in the delay. And this is what we do for each packet. Returning back to this page, so for the first packet in the talk spurt, I'm setting my playout time to the time it was sent plus a playout delay, plus the expected playout delay. So this is like my mu plus some constant times the variance, k times vi. And, well, how do you choose that constant? Well, it depends on your design choice. How much loss can you tolerate, or how much playout you can tolerate? Depends on that. But, so the purpose of that KVI term was to push the playout time far enough into future, right, so that only a small fraction of the arriving packets in the talk spurt are lost due to late arrivals. But I told you before that within a talk spurt, unless we have a silent period, all the packets need to be played with the same playout time, with the same playout delay. So my sound cannot get faster and cannot get slower. So if we are in the same talk spurt, my playout time for the ith packet and the jth packet, my playout delay for them will be the same. I'm still using di plus kvi. di plus kvi. I'm not using dj plus kvj. So this is the time this sound chunk was sent, and I'm adding the same amount of playout delay to play it. But if we are talking about a new talk spurt, let's say a silent period occurred, and one party again started to talk, I am continuously calculating this VI and continuously calculating that DI, and then I can update these playout delays in my new chunk, in the new talk spurt. Okay, any questions? So yeah, don't get too fixated on the formulas here. Well, there can very well be other formulas. But this is just to show the general principle that we need to estimate the mean of the delay, how much delay we have on average, and how much that delay varies so that we can choose a flexible playout time that can adapt to changes in the network conditions. So we discussed how to deal with the packet jitter, right, the changes in the network delay. Now let's discuss how to preserve the quality of the audio call, even if some loss occurs, even if some packets are lost or they arrive later than their playout time. These schemes are known as the loss recovery schemes, and there are many approaches to that. We will see a few examples. So one way to do that is perhaps adding an acknowledgement or not acknowledgement. So every time the receiver receives a packet, it can tell the sender that I received, so you do not have to send it again. Or alternatively, the receiver can say, I didn't receive after a timeout occurs, and then the receiver can repeat the transmission. So this is maybe possible, but this is not suitable. This is not well suited to real-time voice over IP applications, because after all, the retransmissions take 1 RTT, and well, acknowledgement itself, acknowledgement plus the retransmission takes 1 RTT. And if the network delay is high already, well, adding 1 RTT here doesn't really make sense. So we need to look for alternative methods, one of which is forward error correction coding. So I mentioned this a little bit in the wireless chapter. So here, in the wireless chapter, it was applied in the physical layer of the network. But here, we can build it in the application layer. So this can send enough bits to allow recovery with retransmission. So we are adding some redundancy into each chunk, each packet. And then even if some of the bits are lost in a chunk, or even some of the chunks are lost altogether, we can still recover most of the sound. Yeah, so there is some description of it, but let's just go over an example that's better to understand over an example. Okay, so let's say my first chunk is 0, 1, 1, 0, 1, 1. Yeah, it can be longer, but I'm just writing the first 6 bits here. And let's say my chunk 2 is 1, 1, 0, 0, 0, 1. And it goes on like this. So instead of sending these 2 chunks only, I can also XOR them. Now, XOR operation is just addition in modulo 2. Maybe let's also show that. So 0 XOR 0 is 0, 0 XOR 1, or 1 XOR 0 is 1, and 1 XOR 1 is, again, 0. So it's addition in modulo 2. Well, rather than just sending these 2 chunks, I can also send their XOR. So I get 1, 0, 1, 0, 0, 1, 0, and so on. So I send all 3. And let's say one of these chunks are lost during the transmission. Let's say this is completely lost. I can still recover chunk 2 by looking at these 2 other chunks. I just XOR them again. I'm XORing chunk 1 with the redundant sequence. That gives me 1, 1, 0, 0, 0, 1. That is exactly the same as chunk 2. Well, you can apply this to more chunks than 2. You can apply to 10 chunks. And even if you lose one of the chunks, you can still recover that chunk. Well, obviously, if you lose more than one chunk here, you cannot recover. But that's our limit. But it still adds some protection. And it adds that error recovery at what cost? What is our cost? Does it come free here? Anyone would like to tell? Can I just apply this simple error correction coding scheme to all the chunks, all the kinds of data, so that even if I lose some of it, I can still recover? Any costs here? Come on, guys, you know what the cost is here. It's simple. Exactly. You sacrifice some bit rate. Either your chunks get bigger, or you need to send more chunks. Yeah, thanks for the answer. So instead of sending now n chunks, I need to send n plus 1 chunks, increasing the bandwidth by a factor of 1 over n, where n is the number of chunks you apply your XORing. So there is another error correction scheme. By the way, this is just the simplest form of error correction coding, but there are much more advanced methods like convolutional coding, LDPC codes, and those are the topics of the coding theory. But my point here is that in error correction coding, you can potentially recover loss of more than one chunks if you add enough redundancy in a smart way. It's not always recovery of one chunk. So because XORing is the simplest way of error correction coding, but you can recover more if you apply smarter error correction coding with more redundancy. So the second approach we have is piggybacking the lower quality stream to the next one. So let's say this is our original stream, 1, 2, 3, 4. Packets are coming. And instead of these chunks as they are, I'm always adding a compressed version of the earlier chunk to the current one. So instead of sending 2, I'm sending a lower rate version of 1, and I'm piggybacking it into 2. Similarly, when sending 3, I'm sending a lower resolution version of 2 and piggybacking into 2, piggybacking into 3. So this gives me another form of redundancy. So here, even if I lose, let's say, the third packet, I can still play that third chunk, although at a lower resolution, it will still be audible by playing it when the fourth chunk arrives. So this still trades off some throughput, because although in lower resolution, we are still adding more data into every chunk. This can conceal the loss. This doesn't recover from the loss, but it can conceal the loss. And it is not always appending just one chunk. It's not piggybacking just a low resolution version of one chunk to another. You can piggyback multiple chunks. For instance, instead of piggybacking 3 here, I can also piggyback 2 here. I can also piggyback 1 here. So even if I lose all 3 of these, I can still recover all of them from the reconstructed stream of the fourth chunk. But again, this adds on to your playout time. You cannot have a very low playout time, a low playout delay, and recover from all those, because you need to wait for the next stream, for the next reconstructed stream to recover from the loss of an earlier stream. So other than these error correction coding schemes, we also have an interleaving method here. Interleaving is just a mixing up of the order of the chunks. So audio chunks here are divided into smaller units. So this is my chunk 1, this is my chunk 2, this is my chunk 3 and 4. And I'm dividing them into even smaller units. So they were 20 milliseconds earlier each. Now I'm dividing each of them by 4. So they're split into 4 5-millisecond units per audio chunk. And now I'm just mixing them up, again, in a smart way. And our receiver also knows the method of mixing up, so it can put them in the right places again. So I'm perhaps adding each one of these subchunks, let's call them subchunks, into different chunks. So my first one was here. I put my second one here. I put my third one here. I put my fourth one here. So I split them into different streams. And now loss occurs. Let's say one of the received streams is lost, so this is completely gone. Well, although I lost a little bit of it, I can still conceal the loss because I received most of it. And same for all these other chunks here. They lost a portion, but all of them can be played, perhaps a little bit distorted, but it will be concealed from the human ears, possibly. So unlike the previous two approaches, here we do not add any redundancy, and we do not increase the bandwidth requirement. We are still sending the same amount of data as the original stream. So interleaved stream and the original stream are the same size. But it needs to increase the playout delay. Why? Because our receiver has to receive, let's say to play out the first one, it has to receive all four, at least most of these four subchunks, correct? And look where that fourth subchunk comes from. It comes from the fourth packet here. So to play the first one, it has to wait until the end of the fourth chunk, until the fourth stream is received, and then it can play all of them. So you cannot have a very small playout delay and still use interleaving here. So this is perhaps a great method for streaming stored video and stored audio, but for conversational voice over IP applications, this is rarely used. Okay, so any questions on recovery or error correction coding schemes? So we discussed, let's see, forward error correction coding using XORing method, using piggybacking low quality stream into the next one, and interleaving. So these are recovering from loss, concealing the loss, even if the loss happens. Any questions? Okay, so again, these are the principles of recovering from loss. The exact application will differ from use case to use case. Okay, so now we learned a lot of methods, how we store videos, how we stream videos, how we maintain the conversational aspect of sound with attaching sequence numbers, with attaching the timestamps, and then calculating the playout times, the playout delays, and therefore maintaining the conversational aspect of the sound. Now we are looking into the actual protocols, RTP and SIP, that can provide these things. Now we are going more specific. Well, these are just defined in request for comments documents, and these are very widely used. But you don't have to use them when designing an application. But having them enables interoperability between different applications and different devices. So let's first start with the real-time transport protocol, or in short, the RTP. So in today's lecture and the previous one, we talked about how the sender needs to attach the timestamp and the sequence number of, be it a chunk, audio chunk, or video chunk, so that the adaptive playout delay or fixed playout delay can be calculated at the receiver. But how do you exactly add that sequence number and the timestamp? I mean, where in the packet do you add it? What is the format to add it? And how does the receiver know that it is there in the packet so that it can use that as information to select the correct adaptive playout time? And another thing is how to fragment the audio, how to encode video in different formats, how to indicate the formatting of the video so that the receiver can use the correct decoder to decode the video. So all these things are provided in the RTP protocol. It, for instance, provides the payload type identification, be it audio, video, and what type of audio and video, packet sequence numbering, and timestamping to estimate the playout time. So RTP has both the properties of an application and transport layer protocol. Well, it runs in the end systems. It runs on the client and host devices, and it can be controlled by the programmer. So in that sense, it is an application layer. You can say it is an application layer protocol. But it is really classified as a transport layer protocol because it extends the functions of UDP. So it can be, it is usually encapsulated in UDP segments, although you can design an application with RTP over TCP. So, for instance, you can use RTP to transport certain well-known formats of sound and video, like MP3, MP4 formats, or whatever the video formats that we discussed earlier, that H something, whatever formats. But you can also encapsulate proprietary formats of video and audio with RTP. So RTP typically runs on top of UDP. Again, why? Because we do not really need retransmissions in conversational video and audio. And RTP provides the transport layer interface that extends the UDP with the port numbers and IP addresses, just like HTTP. Remember, in HTTP, we have the port numbers and IP address or the host name. Also with payload identification, what format of audio and video, packet sequence numbering, and timestamping. So it looks like this. So RTP on top of UDP here. And you can also run another app. You can run your application over RTP. So I wouldn't judge you if you say RTP is an application layer protocol because it keeps a lot of properties of application layer protocols. But it is, after all, it is classified as a transport layer protocol. So what happens is, so the sending side encapsulates a media chunk. Let's say this is your media into an RTP packet. And then this whole thing can be encapsulated into a UDP segment. And then it is encapsulated into a datagram and then the link layer packet whatsoever. And at the receiver side, each of these are removed one by one to extract the media. And thanks to RTP, our receiver will know all these things, the payload types, the packet sequence numbering, and the timestamping, and therefore estimate the correct playout time, use the correct decoder, and so on. So yeah, we already discussed most of this, what RTP header indicates here. Yeah, I think we can just skip this. So this is how an RTP header looks like. We have the payload types, video and audio, and what format it is. For instance, it has different payload types. For instance, it is 04 PCM MULO type audio. It has packet type 34 GSM type audio. So we need to indicate this again. Why? Because the receiver needs to use the correct decoder to decode the sound or video file. It also has payload types for video. So these are for video. So the next, we have the sequence number type. So in UDP, we do not have ordered transmissions. UDP does not guarantee ordered delivery. But earlier I said you can build applications that run on UDP that will provide some of the services that are not provided by UDP. Things like security, things like ordered delivery. So this is a perfect example of that. Although UDP does not have sequence numbers, it doesn't ensure ordered delivery. We can build RTP on top of UDP to ensure ordered delivery if you need it. I'm not saying it is always guaranteed to have ordered delivery, but if you want, you can build an application that will ensure ordered delivery of packets. Typically, in conversational voice and audio, this sequence number and timestamp together are used to estimate the playout time, right? We just learned about it. Yeah, so we just talked about the timestamp, and we also have this SSRC field. So this is just of the RTP stream. So typically, each RTP stream will have a different distinct SSRC number. So again, my point here is not to learn the exact RTP header format, what's in there. We do not have to memorize any of these. If you are building an application, you can just refer to how RTP works and then integrate it into, understand that, and then integrate it into your application. So just like your socket programming homework. Do you, in fact, need to remember what each HTTP request and response fields are for? Do you really have to memorize all those? No, definitely not. Sorry. But the point here is to know why we need these fields for a real-time application. For instance, you need to understand why we need sequence numbers and timestamps, right? That is for estimating the playout time. You need to indicate why we need payload types. You need to know why we need payload types. That is because our receiver needs to use the correct decoding format. Or it needs to decide whether it can receive the file in the first place. If our receiver does not have, let's say, GSM decoder, there's no point in agreeing on a GSM encoding format when initiating an RTP session. So, RTP does not provide any mechanism to ensure timely data delivery or the quick QoS guarantees. And it is only seen at the end systems, but not immediate routers, right? Just like any other application layer or transport layer protocol, it is only at the end systems. So if your routers cannot provide guaranteed delivery, cannot provide a throughput guarantee or a quality of service guarantee, well, obviously, RTP will fail to provide those. But still, with RTP, you can still build certain applications that will ensure ordered delivery of the packets, for instance, or that will choose that adaptive playout time smart enough so that very few number of packets are lost, and you still maintain the conversational aspect of audio by not having a too high playout delay. Okay, any questions on RTP? All right, so RTP defines the packet structure for real-time audio and video, but in order to make a call or establish a video session, you still need to initiate the session. So these sessions are not just about sending data, but you need the first handshake. You need to inform the callee, the person you are calling. You need to agree on a certain encoding format. And this is provided by SIP, or the Session Initiation Protocol. So just like the other protocols we learned, it is defined in the RFC documents. And it provides, SIP provides functions of notifying the callee how to know the IP address of the callee. For instance, users do not have a single fixed IP address, right? We are not servers. We do not have a fixed IP address. Yes, in the mobility chapter, we learned even if a mobile is moving around networks, we can still route the packets through its home network. But the callee might have multiple client devices in the first place. For instance, I have my Skype application in my phone, in my PC at home, or in my even watch. So all these client devices can be running the same Skype application, same voice over IP application, with different IP addresses. So when someone calls me, how does the callee know which device it needs to route packets to? SIP also provides all these call management functions. So in a call, for instance, you can pause the call, you can redirect the call, or you can hold the call. SIP provides all these supporting functions. So you can think of it like this. So SIP initiates and provides all the management functions. And sound data still is carried over RTP. So let's list all the functions SIP provides. So first of all, it lets the caller to let callee know that she wants to establish a call. And then the caller and callee can agree on the media type and encoding. So the caller will say, I want to send an audio file using GSM format, and the callee will say, okay, I have GSM decoder, so please send, and then the packets will be transmitted over RTP. And they can end the call. Well, SIP services also help you determine the IP address of the callee. Again, it is not just because of the mobility, it is because the callee might have multiple client devices running the same application. And it maps these mnemonic identifiers to current IP addresses. So mnemonic identifiers are like your usernames or SIP addresses. For instance, it is the email address that you use for opening a Skype account. So as humans, we are better in memorizing mnemonic identifiers. So when I want to call someone, I do not have to enter their IP address. I just enter the mnemonic identifier, and it will be resolved by an SIP registrar or proxy into an IP address that the client is using. SIP services also have certain call management functions, so you can add media streams during a call. You can even change encoding during a call. You can invite others. You can transfer and hold calls. So all these support functions are provided by SIP, but not the data transmission. The data encapsulation, the media encapsulation occurs with RTP. So let's give out an example. So in this example, for the time being, we will assume that Alice already knows the IP address of Bob's PC or Bob's client device. And we will look into the problem of determining that IP later on. Okay? So this is Alice's IP address, and this is Bob's IP address. So this SIP session begins when Alice sends Bob an invite message, which is in fact very similar to an HTTP request message, as you see here. But this is usually sent over UDP, not TCP. So just like GET, now we have invite. Bob adds some IP address. So this is using IP4 as the network layer protocol. And then this is Alice's IP address. So the media type will be audio. And the media will be sent over this port number using this protocol. In other words, the RTP protocol. And this AVP0 is the encoding format. And then, after receiving this invite message, Bob's terminal will ring. And if Bob picks up the terminal, that terminal will send a 200 OK message, just like an HTTP response message. And it will say, I am using IPv4. This is my IP address, yes. And I accept RTP using AVP3 encoding format from this port number. And then Alice's client device will send an acknowledgement. So this port number here is the SIP port number. But they agreed on a different port number, different set of port numbers for exchanging their RTP messages later on. And then they will send sound data, sound media files using RTP protocols. So this part is, again, RTP. So notice how the port numbers here, maybe let me use another color here. So this port number is Alice's port number when she requested to receive RTP over a certain port. And this is Bob's port number when he requested to receive audio from that port number. And again, this this encoding format, AVP3, that is the GSM format Bob is receiving, and this encoding format, AVP0, is the MULO format Alice is receiving. So they agreed on everything prior to the establishment of an RTP session using SIP. And once they agreed on everything and exchanged acknowledgements, then RTP session is established and they send media files. So in some sense, we can think of RTP as an out-of-band protocol. So these call management functions are not sent within our actual media transmission, but it is out-of-band. It is occurring separately. They are sent and received in sockets that are different than RTP sockets. And as you also noticed here, that RTP messages are human readable in ASCII format, just like HTTP. So my aim in showing you this is not to ask these details in the final exam or anything. Let's just be clear on that. But this demonstrates the call management, how we can provide these call management functions, how we can agree on the media types, and so on. A few more comments on what we saw in the previous example. Well, suppose that Bob doesn't have the PCM MULO encoder. So in this example, Alice said she will send AVP0, right, using MULO audio, requesting MULO audio. Well, if Bob doesn't have MULO audio encoder, then he won't be able to send it. So instead of sending 200 OK in that case, Bob will need to respond with 600 not acceptable. So just like HTTP's 404 or 500 type of messages when the requested object is not there, or you send a bad request, Bob will instead reply, not acceptable. Again, that's just an example. Alice will then send a new invite message, perhaps advertising a new encoder. Bob can also reject a call, and Bob can set up different responses for different caller IDs. For instance, if Bob's boss is calling before 6 a.m. in the morning, he can just automatically reject the call. And the media can be, again, media is sent over RTP or another protocol, doesn't matter, but it is agreed on in the SIP messages. What protocol to use, what port number to use, what media format to use are all indicated in the SIP messages, and then the actual media is sent over another protocol. So in the earlier example, I said that we assume Alice knows Bob's IP address. But in practice, that is not the case. You do not know the IP address, at least your client device does not know the IP address of your friend who you are calling over Skype. But instead, Alice knows Bob's SIP address. That's how you add your friend over in Skype, right? You add their email address into your Skype client, so you know their SIP address. So in this example of the SIP message, Alice knows Bob's SIP address, which is bob@domain.com, but not Bob's IP address. So this is an email-like address, and it can in fact be an email address. But it can also be Bob's phone number, depending on the application. And because Bob's IP is not included, this will incur queries to intermediary SIP servers to resolve Bob's client IP address. So Bob may have multiple client devices, each running this application. So in this case, the SIP message will look like this. So it is coming from alicehereway.com. This is Alice's SIP address, to bob@domain.com. And this is the caller's ID, content type, content length, whatever. And it will also indicate that Alice will need to send this audio on a certain port number using RTP protocol using AVP0 format. So this is just syntax. But the point here is that Alice specifies in the header of the SIP message the SIP address of the destination and receives SIP messages over UDP. So this content provides information about Alice's IP address so that Bob does not have to look out for Alice's IP address. Yeah. Okay. A few notes on why we need to get the IP address of the destination again. Here, we may need to obtain IP because, first of all, the user moves around. Yes, in the mobility chapter, we learned we can still go through the home address, but the user might have multiple devices, as I said, that are running the same application, and each of these devices might have different IP addresses. And the results of the SIP response to Alice's query can be dependent on the time of the day. It can be dependent on the caller or the status of the callee. So for instance, I can direct a caller to my Skype client application in my workplace during some time of the day, and I can direct them into my mobile device during another time of the day, depending on where am I. So these requests of obtaining IP addresses by Alice using the Bob's SIP address will incur a query to the SIP proxy servers. And this proxy will respond with an SIP reply telling Bob's IP address, the IP address of the Bob's client device. But how does an SIP proxy server determine the current IP address for bobdomain.com? Well, we have SIP registrars. So in fact, there is a good analogy between the proxies and registrars of SIP that comes from the DNS. So SIP proxy is like SIP proxy servers are like local DNSs. You send your request for resolving an IP address of the client, SIP client, and you also have SIP registrars. And these are like authoritative DNS servers. So the DNS server translates the fixed host names to fixed IP addresses. And just like that, SIP registrar translates fixed identifiers like the SIP address and the phone numbers into dynamic IP addresses. An SIP proxy is the first point of contact where you send this message to resolve an IP address of an SIP client. But how does an SIP registrar know the IP address of Bob's clients? So it goes like this, right? So Alice sends to SIP proxy to resolve the IP, and SIP proxy sends that request to SIP registrar, and then SIP registrar will reply back to SIP proxy, and then it will go back to Alice. But how does the registrar know the IP address of Bob? Well, whenever Bob's client devices get active, perhaps turned on, they will send this register message to the SIP registrar. So it will register perhaps this SIP name, within this SIP domain, this SIP name, and it will indicate the IP address of that. So whenever a request comes for bob@domain.com, it will return the IP address indicated in this register message, and some expiry. Yeah, I already mentioned this proxy function. So Alice first sends the invite message to her proxy server, and it will contain the address of Bob. That proxy is responsible for routing SIP messages to the callee, possibly through multiple proxies, in that case, SIP registrars. And Bob will send the response back through the same set of SIP proxies. And SIP proxy is analogous to the local DNS server. And sometimes these SIP registrars and proxies are on the same servers, so they can be co-located at times. Okay, so let's just work it out over an example. So let's say this is perhaps Alice and this is Bob's client devices. And let's assume that Bob's client device is turned on and it registered with the Eurocom SIP registrar. So it sent already a register message to here. So for the sake of this example, okay. So we already have actually these SIP addresses. So let's not say they are Alice and Bob, but let's say they are Jim and Keith. Okay. So for the sake of this example, let's assume that Keith is registered with the Eurocom SIP registrar. Okay. So first thing is, because Jim doesn't know the IP address of the Keith's SIP client, Jim will first send the invite message to the UMass proxy server. So this is the proxy server closest to Jim, perhaps. And then this proxy server will forward that request to the Poly registrar server, perhaps because Keith is in that domain, in the Poly SIP domain. But Poly SIP registrar does not know the current IP address of Bob's client device because Bob recently registered with another registrar. So in that case, Poly server will return a redirect response indicating that it should try another SIP registrar at keith@eurocom.fr. And then this UMass proxy will forward that request to Eurocom registrar servers. The Eurocom registrar will forward that invite to Bob. And then SIP response is returned to Jim using the same route. So this is very similar to how DNS works, how we use DNS to resolve IP addresses. But here we are resolving the IP addresses of SIP clients. And we only have SIP proxies analogous to local DNSs and SIP registrars analogous to authoritative DNS servers. And then when Jim and Keith, in fact, do communicate, do send media files, because they now know each other's IP address, they agreed on what kind of encoding they want to use, they can just send media files, media packets between each other directly using perhaps an RTP protocol. All right? Any questions here? Any questions on the lecture today? I think we can stop here. Okay, so as I said, we are learning too many protocols here. And this lecture is a bit heavy on the application layer protocols. But our purpose here is not to memorize anything in these protocols, but basically to understand how we can send over media and how we can send over audio and video over the web, but still provide these guarantees required by such applications, how we can structure messages to enable that, and how we can configure the web servers, the routers in the web, and client applications to help with that. So again, this is not, most of this won't be in the exam. I mean, the minor details of everything won't be in the exam, but if you understand why we use these things, but not else, but not something else, why we do things in a certain way, but not other, I think that should be fine. Okay, then I'll see you on Friday.